Live from the North Carolina Museum of Natural Sciences in beautiful downtown Raleigh, it's the Science Cafe with your host, Chris Smith.
All right, everybody, let's get tonight's program started. Good evening, everybody. Welcome to the Science Cafe. I hope you're excited to be here. All right, cool. That's just my way of getting you to clap for me. Thanks for coming out to our program tonight. You know, we're here every Thursday night at 7 o'clock for the Science Cafe, bringing you all kinds of incredible speakers on great topics across all STEM, science, technology, engineering, mathematics disciplines. And tonight is no different. We've got a really exciting program coming up for you this evening. Tonight's program is part of the Liftoff NC campaign. This museum, the North Carolina Museum of Natural Sciences, and a number of other science and cultural institutions all over the Triangle are all working together to celebrate the 50th anniversary of the Apollo moon landing, of the Apollo 11 landing. So on your tables, you probably saw it, the orange and blue Liftoff NC flyer. On the back of that, there's a list of events. There's lots of cool stuff happening here at this museum and for the rest of the year, all centered around celebrating the Apollo moon landing. So make sure that you check out what's going on. There's lots of cool stuff, including a third Science Cafe in July, again on topics of celebrating Apollo and the moon. That'll be here at the Daily Planet Cafe again. So, right, take this home, get out your calendars, put everything in. You're going to want to be at this museum or at our partners for Liftoff NC events. We're having a lot of fun. Also, housekeeping. You have surely noticed the blue sheets of paper on your tables. That is a fact sheet to give you some information about a research study that the museum is sort of helping out with. So after tonight's program, you'll get another sheet of paper, a second one. This is one for you to get the knowledge, and then we're going to give you a survey form after the cafe tonight. It'll take about 5 minutes for you to fill it out. It'll really help us. It'll really help this research team. They're doing a national study of events like this Science Cafe. So help us out, help them out. We want to make sure that everybody's getting the best science learning and events that we can possibly do. Now, tonight's topic, the science of the moon. We have planetary scientist Dr. Brett DeNeve from Johns Hopkins University's Applied Physics Laboratory. And this one's going to be special, I think, because who looks up at the moon, right? How many of you have looked at the moon through a telescope? Like you've gone back, okay, yes, beautiful. I remember being a little kid and the first time that I looked at the moon through a telescope, right? That first time that I got that really crystal clear image of the moon. Full moon, bright disk in my toy store telescope. I mean, it was not a good telescope, but it was so exciting to look up and see the moon. Now, imagine being a planetary scientist and you get to look at images coming back from the Lunar Reconnaissance orbiter cameras. How cool must that be, right? So, I hope you think it's cool, and I hope you're ready to, obviously I do, and I hope that you're ready to learn a little bit more about the moon through the decades with tonight's guest, planetary scientist, Dr. Brett DeNeve.
All right, thank you. All right, yes, thank you so much. I'm really excited to talk with you about the moon tonight. It's my favorite topic to talk about, the science of the moon. And it's kind of a lofty title because the science of the moon is something we could talk about, months, years, and not finish. But I wanted to give you a little bit of the kind of broad brush highlights that we are studying now, especially with the Lunar Reconnaissance orbiter. I work on the camera team for that mission. It launched around 10 years ago and is going on its 10th year, still in orbit, collecting images, radar data, thermal infrared data, all kinds of things of the moon, pretty much nonstop. So I wanted to give you a brief overview of the history of lunar exploration because lunar science is really tied to lunar exploration. So the timeline that I'm showing up here from the dawn of the space age around before 1960 up through today shows a line for each mission to the moon. The gray lines are orbiters or flybys. The blue lines are landers, robotic landers, and the red lines are times that humans landed on the moon. So we look back in this early era of space exploration, just getting the very basics down of the moon. The image on the left is the first image of the Lunar Far Side. You can see that is a bit fuzzy, grainy, not looking so good, but it was enough to know that the Lunar Far Side is quite different than the near side. And so this was from a Soviet orbiter. And since they were the first to see the far side, they got to name some of those features. So some of the dark splotches on there are Mare Moscoviense, the Sea of Moscow, Tsiolkovsky for the famous rocket scientist. And then going into just a whole huge number of precursor missions that were all leading up to the Apollo program. And these were really an important part of the Apollo program, understanding what is the surface of the moon like, how do we land on it safely? And really also, where should we land? What are the interesting features we want to understand? So moving into those 6 red lines, those are the 6 Apollo missions to the moon. Starting with Apollo 11, of course, one of the reasons we're here tonight is, celebrating the upcoming anniversary, the 50th anniversary of the Apollo 11 landing. And then going through Apollo 11, 12, 14, 15, 16, and 17, the missions became increasingly complex as they went along. And another anniversary that will be coming up in a few years is the 50th anniversary of Apollo 17, also the 50th anniversary of the last time someone was on the moon. A bit more melancholy of an anniversary, and when I talk to kids a lot, I tell them, when do you think people were last on the moon? A lot of people say, kids think last week, that's where the space shuttle goes, right? But no, it was before you were born, and probably before every one of your parents was born as well. So it's been a while. And then we move into 1976. That was the last of this era for landers on the moon. This was the Luna 24 sample return mission. And then we get to this long, bleak period in lunar exploration. This is the lunar doldrums, where for decades there were just a couple missions to the moon. Those 2 lines indicate 2 NASA missions. Clementine is actually joint with the Department of Defense, a kind of technology demo. And then the Lunar Prospector mission. And happily, we are now moving into the Lunar Renaissance, this time where we have seen a lot more activity at the moon. We have a whole slew of international missions as well that include Japanese missions, Indian mission, US missions, of course, and Chinese missions. So the 2 missions that are still active now, if I can use the pointer, are the Lunar Reconnaissance Orbiter, which I mentioned, and what a lot of the data I'll be talking about is from. And then this is Chang'e 4. This mission is with a small rover named U-2-2, following on U-2-1. And it's now currently on the far side of the moon, operating, roving around Von Karman crater. This was the first lander of any type on the far side of the moon. So what have these kind of more recent missions really concentrated in the last decade given us? One of the things they gave us is context. The Apollo missions and a lot of the early missions gave us a lot of detail about a few areas on the moon, but we didn't even have the best global imaging. So this is a data set that was created from thousands and thousands of individual images, just giving us this incredible view of the moon that you can continue to zoom in on. We're also getting context in the form of gravity data. This is showing a derivation of some gravity data that highlights areas where you have a big change in gravity. So areas that have more massive or more dense portions of the crust, or that have a mass deficit where a crater removed some of the crust. Those show up differently in terms of the gravity of the moon. And so this is really the best map of any gravity of any body in the solar system, including Earth. We have global topography data too. Hopefully you're starting to notice, the big differences between the near side, which is on the left, and the far side on the right. The near side has a lot lower topography, a lot lower altitude, pretty much overall. The far side has a much thicker crust. And then thorium and titanium. If you look at these different element maps of the moon, they show that there's big differences in the history, the geologic history of both the near side and the far side, that we're still trying to understand. Why is thorium concentrated on the near side? Why is titanium concentrated on the near side? And these happen to be the areas that all of the Apollo missions went to. So while we visited a lot of places and understood them, we still don't understand the whole global context that they fit into. But we're not just looking at the global picture. With the Lunar Reconnaissance Orbiter, one of the main reasons that it was launched was to start to understand the details of the moon at very high resolution in order to plan for future landings, both robotic and human landings to the surface. So as an example, hopefully you can see on the monitors here, if we add some labels, this is the Apollo 12 landing site. So our goal was to obtain mission images of the moon at resolutions that are high enough to plan for future missions. That also means that we can see the old missions, what was left of them on the surface. And so let me get the arrow again, hopefully. Yes, this is the descent module. If you zoom in close enough, you can actually see the 4 footpads around that. Some of these dark lines are the areas where the astronauts walked, kicking up dirt as they went by, so that's why those areas are darker. And you can see the equipment they left behind, a seismic station. Probably can't see it at this resolution, but there's the flag. When we take images as the sun moves overhead, we can see the shadows of the flags moving around. So we know that all of the flags are still standing except at Apollo 11. And so one of the things that I want to hopefully communicate tonight is all the great reasons that we do want to go back to the surface of the moon. We don't want to have another era where lunar exploration stops and we stop kind of progressing our understanding and our knowledge of the moon. And one of the things that I hear often is, well, isn't the moon just really boring and cratered? We've seen it all. We've seen craters. Why do we need to see more of them? Well, yes, the moon is cratered, and that is one of the reasons that it makes it so scientifically important and interesting. I'm highlighting here in orange, these circles are indicating every crater on the moon that is larger than 5 kilometers in diameter. So you can see some intrepid graduate students did a great job of mapping out every crater on the moon here. And I'll zoom in on one particular crater. This one is large enough, over 1,000 kilometers across, that it's called a basin. And the one in the center here, this big one, is the Imbrium Basin. And if this basin had occurred on Earth, it would have vaporized all of the Earth's oceans, and it would have sterilized the crust down to hundreds of meters depth. And so what is so fascinating about being able to study these basins on the moon is that an equivalent basin surely did occur on Earth. There were numerous basins like this. We just have no record of them because our plate tectonics, our weathering, erosion erases all of these basins. So what we have on the moon is our nice little partner in space that's showing us this incredible record of the bombardment history through essentially the entire solar system's history. This basin, the Imbrium Basin, We've dated it. It's around 3.84 billion years old. And you can see the ages of some of these other basins here too. You might wonder how we know these ages. These are the stars to the locations of the Apollo landing sites. So we actually went to these areas, found rocks that we think came from a particular impact event. This is Jack Schmitt here at the Apollo 17 landing site, sampling the Station 6 boulder. This is another view that was collected more recently of where this boulder had rolled down a massif. This is the same boulder that Jack Schmitt was at. Probably can't see it on these monitors, but if you do look up close, you can actually see the tracks of where the rover drove up and stopped right there. But so they chipped off a piece of this rock, dated it with radiometric age dating techniques, and found an age because that rock was collected right here next to this basin, Serenitatis. They dated the Serenitatis Basin, we think. And what is so puzzling and important about all of these ages is they're all around 3.9 billion years. And that is exactly the time that we think life was emerging on Earth. So I told you about, the truly catastrophic effects that each one of these basins would have had on the Earth and surely did have on the Earth. And these were all happening, our biggest lunar basins, in quick succession, all right around this same period in time. So this is what is known as the lunar cataclysm hypothesis. And a huge, broad swath of scientists are interested in this precisely because of its effects on Earth, not just for emerging life around that time, but also for delivery of water to the Earth through comets and water-rich asteroids. So understanding this and testing this lunar cataclysm hypothesis is really important. And that is one of the things we've been working to do. A colleague of mine, Heather Meyer at the Lunar and Planetary Institute, and I mapped out all of these yellow deposits. This is showing the moon rotated a bit. This is the Oriental Basin. It's actually on the western limb of the moon, pretty much out of sight from Earth, but you can kind of get a glimpse of it there. And the yellow deposits are called light plains deposits. And these are deposits that form through ejecta and mixing of materials that were thrown out from this enormous, this one's around 900 kilometers across this basin. So when this impact event occurred, it really scoured essentially a hemisphere of the moon. You can see how these deposits kind of line radially away from this impact event. And so why this ties into what we were just talking about, if you look at the Imbrium Basin here and its position relative to all of the Apollo landing sites, they are definitely within this area that would have been totally scoured and affected by the Imbrium impact event. So what that has led us to kind of reconsider again is whether or not we actually know the ages of any of these basins. We may have been going around at all of these different landing sites not far away from the Imbrium Basin, picking up rocks that were affected by this same impact event, and we are just dating the same event over and over again. So we have two really important ideas here. One, this is the youngest big basin, Imbrium, that formed. The other is that we had a whole series of events that were just pummeling the moon and Earth late after most of the impacts should have stopped. This was well after the solar system should have quieted down, the biggest materials should have been accreted into the planets. So this is one of the big things that we are still interested in understanding. And so how do we go about really testing this and getting the ages for new basins that haven't been affected? Well, one, we can go to the Oriental Basin that I just showed you. You can see the inset hopefully showing Oriental. And these are the peak rings of Oriental that were uplifted by that enormous impact event here and here. I'm going to zoom in on this area. And now we have images that show us just at the outcrop scale. There's boulders here, and hopefully you can see a bunch of them have rolled down. So now we can go, and if we say we want to know more about this one particular basin, we can point you to the exact rock we want you to go pick up to understand that basin better. So sampling and having the context for those samples is a lot easier now that we have this incredible treasure trove of data that's been collected in the last decade. So I've told you about one of the big ancient craters on the moon, but impacts have been pummeling the moon for billions of years now, continuing into the present day. I always have to share this image because I just think it's so beautiful. This is of a pretty small crater. It's around 1,400 meters across, but it's remarkable because it formed so recently. And recently, in this case, is probably less than 100,000 years ago. So the moon is changing and being affected by impacts, but it's still at a rate that is slow enough that you can preserve beautiful features like this. In another 1 million, 2 million years, this crater will look very typical, boring, blend into the background as the space environment, the solar wind, micrometeoroids bombard it. And one of the other things we learned from craters like this is the ejecta process. We can't simulate impacts in the laboratory at velocities like these craters form at. This probably formed from an impactor that was coming in at around 11 kilometers per second. So the best we can do in the lab is a measly 5 kilometers per second or so. So we don't get this full spectrum of what happens at really high velocities. But you can see this is another view of that same crater, just looking down at its ejecta deposit. And it almost looks like it's, still in motion. We can understand how these deposits affect the surface. And then moving into even more recent times, in the last 10 years that the Lunar Reconnaissance orbiter has been around the moon, we've been taking images of the moon, and then we've been taking images of the same spot on the surface again when we come around later when the lighting is about the same. And what we are looking for in those cases is what you are seeing here, new impact craters that have formed in between the time those two images were taken. So it's blinking back and forth between a before and after image where you have around a 12-meter crater. But if I advance here, this is actually showing the before image divided by the after image. So you can really see how the surface has changed. So the crater itself is just this tiny, tiny dot in the middle, but this single crater has affected the surface with its ejecta deposits over 1,800 meters away. So this is way, way farther than most people had thought previously, and it's changing our understanding of the way the surface of the moon is altered over time. It's gardened. And so we think it's happening over 100 times faster than previously thought. We used to think the astronauts' boot prints would last maybe 10 million years or so on the surface. Now we think they will only last 100,000 years. It's still a while. And then I've just thrown this in for fun too. We can also see craters that have been formed on the moon, even more recently. This one is from April 11th, I believe. This was the impact site of the Bereshit, what was meant to be a soft lander by Space IL. This was going to be the first soft lander by a private company on the moon. They were part of the Google X Prize. Unfortunately, the solid rocket shut off early, and so it hit the surface really fast and at a very low angle, around 10 degrees, just kind of coming and skimming the surface. So what's flashing back and forth here is the before and after of the sad demise of Bereshit. But, they're going to try again. One other thing I wanted to talk about, really the two most important things the moon gives us are, number one, this history of impact bombardment throughout the solar system that is lost on the Earth but preserved on the moon. The other is the history of planetary crustal formation. How does the surface of a planet form? And when you're looking at the moon in this kind of perspective, what you see is light areas and dark areas. The light areas are really just the ancient, earliest crust that formed on the moon right out of, it came from the magma ocean. The moon was once molten shortly after it formed, and then differentiated crust, mantle, core. So that lighter area, that's the most ancient terrain, around 4.5 billion years old. The darker areas are all volcanic deposits. And these are the maria, or seas, that are now known to have formed from seas of lava. And the way this lava forms, and actually the composition in a lot of respects is similar to the way lavas form on Earth. Down here, this is an eruption from the latest big eruption in Hawaii. If you're a planetary geologist, you get to go to Hawaii and study lava flows a lot, try and understand how they occurred on the moon as well, because hopefully you can see some of the outlines of this kind of ancient lava flow, over 3 billion years old. But if you see the shapes of it, they follow these same kind of flow patterns as occurred in Hawaii. These are same composition basalts. In some cases, they erupted a lot hotter than you typically see on the Earth, and so they're a little bit less silica. They flow at a higher temperature faster, and they actually form these rivers or channels of lava. So each of these little sinuous regions is what was once a river of lava that flowed up to the north here and filled in this entire region with a smooth lava deposit. One of these rills, as they're known, lava channels, was the site of the Apollo 15 landing site, which there is an arrow. I think it's right there. I can't see even from where I'm standing. But so these are really interesting features that have been studied in detail. Some of the volcanic features that have not been studied at all are of unusual composition. Data from the Lunar Reconnaissance orbiter has recently showed us that these two features, these are the Gootizen Domes, are made out of granite, a really silica-rich rock. And on Earth, those types of granites, they form at subduction zones where you have remelting of the continental crust. On the moon, a one-plate planet, no plate tectonics, no equivalent continental crust. How do these form? We really don't know, so it would be wonderful to go get samples of these as well and figure that mystery out. Those are still ancient features, well over 3 billion years old. And now there's a quick video. This is created from a digital terrain map of the surface, so showing the elevations, and then we've overlaid our image on top so we can kind of zoom around, because this is a really strange feature. I can't show you a picture of a similar feature in Hawaii that formed and can tell us how this, give us an example of how this may have formed. We really have no terrestrial analogs. Our best guess now is that this overall area here is a collapse, like a caldera. And this rougher area around here was the caldera, that's now the caldera floor, kind of jumbled up. And the interesting part is these mounds or regions on top. One of the models for how these formed were just the very last dregs of volcanism. So basalts flowing out and puddling on the surface there. The weird thing about these is that they have very, very few impact craters on them. So that's how we date a surface on the moon. In general, if we can't go and get a sample, we count the number of craters on it. If it doesn't have very many, it's young. If it has a lot, it's old. So this surface dates to around 100 million years. And that might sound old still, but if you're thinking that all of lunar volcanism essentially stopped well over 2 billion years ago, this is more or less yesterday. We can't explain it with our thermal models. The moon should have cooled off enough by then. It shouldn't have any more heat enough to remelt its interior and produce this volcanism. So either we don't understand, we're wrong, we don't know the age of this thing, it's actually ancient, but something is fooling us into thinking it's younger, or we don't understand the thermal history of the moon, and volcanism actually has continued up until almost today. And then one last thing I wanted to leave you with is a look at the moon's south poles. You may have heard that we're considering going back to the moon, or as a colleague of mine likes to say, going forward to the moon. But this is the plan to return to the moon with the Artemis program. Artemis was the sister of Apollo, and land the first woman and next man on the moon. The current date is 2024. We'll see if that happens. But one of the reasons that scientists are really excited about this is because they want to land near the moon's south pole. And what you're looking at here is a region that's just around the pole from around 88 to 90 degrees. And this is an illumination map. So everywhere that is white sees the sun nearly all of the time. Everywhere that is black sees no sun ever. And the reason it can be like this is, you know, the Earth's tilt on its axis is around 23 degrees. So the north and south have, 6 months of illumination and 6 months of darkness. On the moon, the tilt is only around 1 degree. So anything that is a hill at the pole will stay illuminated nearly eternally. Anything that is in a low, like a crater, will be in permanent shadow. So all of these black areas are known as permanent shadowed regions. And this crater here is Shackleton, which I'll point out because we're going to look at another view here of Shackleton Crater, de Gerlache over here, and the arrows are pointing to some ridges. Both Shackleton and this ridge right here have been identified as one of the prime targets for our next lunar landings. And the reason for that is, first, in this ridge, you have nearly eternal sunshine, and that is wonderful for power. You don't have, at the equator on the moon, you have 14 Earth days of daylight, and then 14 Earth days of darkness. That a moon's day is 28 Earth days. So that, you can imagine, long period of darkness, 2 weeks of darkness, is really challenging for any power, solar power. You have to bring nuclear power with you, or in big batteries. But these areas too have proven to be really fascinating because they are so cold. They trap any volatiles or water. So we've done a lot of different kinds of measurements of these permanently shadowed regions, and there are a lot of good indications that there is actually water ice in these really cold regions. Fantastic for science. How did it get there? Was it comets? Was it eruptions of the moon's internal water that came up with volcanic eruptions? So we'd love to go and understand that water. And it's great for, really for exploration. It's a resource. You can, if there's enough water there, that can be used for astronauts, breaking apart into oxygen for breathing, or for drinking water, or for rocket fuel. LOX hydrogen fuel can be created from these sources. So I wanted to leave you with a view of what the rim of Shackleton Crater looks like. This is in about the dead of winter at the South Pole, so the smallest amount of light it gets nearly, but you still have this beautiful ridge of illuminated terrain kind of floating out of the darkness. And these are the peaks along that other ridge that I showed you. So hopefully before too long, humans will return here and start to kind of unravel a lot of these interesting puzzles that the Apollo program has left us with. All right. Thank you.
Let's give her a round of applause. Thank you very much. All right. So now it's time for the question and answer session. So we just learned a lot about the moon, Lunar Reconnaissance Orbiter. We saw some incredible pictures, learned about your research. Now we're going to flip it, and you get to find out what we want to know on the other side. So yeah, the way it works, if you've got questions, raise your hand, wave at me, and wave at my partner Anu over here. She's got the second microphone. We'll move the mics around the room and around the moon. Did I say that? I did. That's fun. That's fun. And we'll get to as many questions as we have time for. We'll get started right over here.
Hi. So how did it come to be that the rate of rotation and revolution of the moon are the same, so that one side is always facing us? How did that come to be?
Oh, I should really learn more about this because people ask me this all the time. And my answer is something like, well, you know, orbital mechanics, tidal locking, something. And yeah, it's really just a gravitational effect that the moon was once closer to the Earth and it was rotating faster than it rotates now. And the interaction of the two bodies eventually slowed down the moon enough, and then it kind of gets stuck in this rotational pattern. And maybe if I gave you a fancier answer, no one would care anyway. But that's my non-orbital dynamic expert opinion.
And if I can ask a second question,
yeah.
Why is the far side of the moon so different than the near side? Is it because the Earth is in the way capturing?
No. But that is a great question, and that's still one of the things that we want to understand. I was just talking about this with a bunch of colleagues recently, and we went through all of the different theories. There's all kinds of theories. One was, the moon used to be closer, and so it was getting heat from the Earth, and so it didn't solidify as quickly. And so that meant most of the crust formed on the other side, and the near side stayed hotter longer. But the weird thing is that there's this huge compositional difference, not just in the volcanic deposits, but in radioactive elements. So there's thorium, which keeps volcanism going longer because it's a heat-producing element. So that's why we think a lot of the volcanic deposits are on the near side of the moon, because there's a lot more thorium to keep that volcanism going, keep the heat. But why is all the thorium on the near side of the moon? We don't really know. There's all kinds of weird theories about this. There was a second moon at one point, and it kind of slowly smashed itself onto the far side. Or, you can come up with any kind of weirdo theory, but none of them at this point are really what we would have a testable hypothesis. One of the great things would be to go to the far side of the moon, which we have never been, to that ancient crust. Even the U-2 rover that is on the far side now, that's in a volcanic deposit. If we could go to that ancient crust, very pristine compared to how it's been bombarded on the near side, and pick up that rock and bring that back, that'd probably start to give us some of the answers. Oh.
So I have a couple questions related, though. So they dated these rocks, right? How was that done? Carbon isn't going to work, right? Mm-hmm. And then the other one, I presume. And the other one is, did they collect samples from any other regions and date them, just for comparison? Yeah,
so they do this through a study of the different isotopes and their various levels. So lead, uranium is one method. Argon, all different isotopic systems that you can look at to kind of try and get an age. And I used to think that these radiometric age dates were like, it's perfect science, and they give you this number and they have pretty small error bars. And then I started getting into the details more of how they do it, and oh my gosh, it's really kind of a mess the older you get into some of these rocks that have been really beat up. But yeah, rocks, it gets better with the younger volcanic rocks that are, 3 billion years old instead of 4.5 billion years old. But so we've dated rocks from all of these different sites and then counted the number and size of craters at each of these different sites. And that's how we work out ages for sites we haven't been to yet. We kind of extrapolate. Well, this site was this old, it had this many craters. Now, like that young volcanic feature, we're getting down into this one has very few craters, so it could be as young as this. But there's a lot of gaps in our timeline of the moon. For example, we have essentially no samples in the middle history of the solar system from the moon. Nothing between 1 and 3 billion years old. So that's a big chunk of history to just kind of extrapolate through. And it's not just for the moon. The moon is the only body that we have all of these samples collected from a known site, and then we can look at how many craters form there. So we take the moon's chronology and we extrapolate it through the entire inner solar system. Mercury, well, Venus doesn't really have any craters, so it doesn't count. Mercury and Mars are the two biggest ones, as well as asteroids. So we have these kind of startings of an understanding of the timing of events in the solar system, but we don't have enough samples to really have a good idea, and then it gets even fuzzier when you try to apply it to other bodies in the solar system. But it's the best we can do now.
Hello. Did the major impact events affect the lunar orbit?
Yeah, a lot of them likely did at least affect its rotation. So early on, I've seen this cool video, animation, I guess, that a friend of mine made showing, different models for how the moon's, its rotation would have changed. And so the near side and far side have flipped back and forth, most likely. When it's not just impacts, when this huge volcanic center formed on the near side of the moon, that affected the moon's overall gravity and shape. So that would have kind of thrown things off. And it can wobble all over the place, eventually kind of coming back to rest. At least that's what the models suggest.
Hi, thanks. One rather depressing point when you were noticing the old modules we have on the moon, you do realize that the first thing we did on the moon was litter. My question.
It would have been tough to bring that all back with us.
I was just listening not too long ago about the migration of Jupiter. And there's a hypothesis that it may have come towards the sun, but Saturn's gravity kind of gave it a, whoa, hold up, and so it ended up in its current orbit. The subsequent thing, though, is that it disturbed the asteroid field. Mm-hmm. And is there a correlation between that, the late heavy bombardment, and what you see in the artifacts on the moon?
Yes. Okay, so you just dove into the heart of this really complex problem. Nice job. It kind of goes a couple ways. One is that all of that bombardment around 3.9 billion years ago, that is, that we think we have seen from the Apollo samples, that actually led to the models that you're talking about, for example, the NEAS model, because it's a real puzzle. It's called the late heavy bombardment. 3.9 billion years is late in solar system history. Why do you have all of these enormous impactors going through the inner solar system at that time? There's no real reason they should still be around. And so people came up with models, like the most famous one is called the NEAS model, that, Jupiter and Saturn went into a resonance, Neptune's orbit started sweeping outward, and then that just totally threw off the entire Kuiper belt, the outer solar system. It sent these impactors raining in, not just to the Earth-Moon system, the entire inner solar system would have been affected. On the moon, it's called the terminal cataclysm hypothesis. In the rest of the solar system, it's late heavy bombardment. And so it's kind of this mix. we started with this observation of all of these impact events on the moon happening at around the same time. And that led to all these models, and it kind of led to all these other observations that seem to support that, but it might be starting from a flawed premise. If in fact we haven't dated all of these individual basins, we've actually seen just the overprinting of ages from one big impact event. So that's why this is such an important question, because it's not just the moon, it's the whole solar system. you know, so that is, it's consistently up there with, this is the problem we need to figure out first by getting samples from the moon.
Hey, good evening. So you showed that one slide that had the gravity differentials on the moon, and I thought that was really interesting. So did I hear you say earlier that volcanism is something that produces that?
Yeah,
Or-
volcanism and impacts.
Okay. So can we compare the difference? Are those kinds of gravity differentials existing on Earth and other bodies in the solar system?
Yeah. So, okay, there's a bunch going on here too. This is a great question. So, the reason we can have this incredibly high resolution gravity data of the moon is because there were spacecraft, twin spacecraft, measuring their precise distance apart from each other, and they were in really low orbit. And so that distance was affected by the pull of each part of the moon as it went over. So spacecraft can't orbit that close to the Earth because there's an atmosphere. Same with Mars. So it really is the best data set, although we know, there's all kinds of other, there's enough known about the Earth, Mars, et cetera, to understand some of the gravity differences. But it'll take forever to scroll back to that slide. One of the coolest things about that was that something that was not expected, was not seen in just from the surface data at all. I feel like it's worth I'll just click back while I'm talking. Or if somebody can just make it go back somehow. But there were these enormous cracks in the moon that are buried. Go back really quick. I'm gonna go past it now, huh? I know, it's way far back. Almost there. I just want to show you these cool cracks in the moon that are hidden beneath the crust. We see no evidence for them on the surface. We're almost there. Almost there. One more. All right, yes. So there's these giant features. They're almost in a hexagon shape. And they go down here and across. And so this is kind of tying into why is there so much volcanism on the moon. It still doesn't fully explain why there's a difference, but we think that these big lines are enormous fissures, dikes, that just fed this volcanism on the moon. And it really lines up quite well if you blink back and forth between these two with where the major volcanic deposits are. So we're kind of getting this peek down into the crust of the moon, seeing where there's actually, those are gravity highs, because dikes would have had this kind of thicker, more dense lava in there. So, yes.
Yes. Does your research shed any light on the collision theory of the formation of the moon?
Yeah, no, it hasn't. I do everything after the moon got to being a moon. Once it was there and it was a magma ocean, molten ball, that's when I start caring about the moon. My research isn't like anything before that. Oh. But yeah, I guess the answer is no. We can talk about the collision formation more if you want.
So this was more a question about the Earth than the moon, but maybe you know a little bit why it seems that life on the Earth started at a time that coincides with these cataclysmic events on the moon?
Yeah, that's a really important question. I mean, it's hard. We think that, prior to that, there might have been life if there was a quiescent period, but these impacts would have just totally obliterated it. And what we're seeing is life emerging right at the tail end of this horrible cataclysmic period, if it existed. But yeah, so why precisely then, I think, is because that is when the conditions started to allow it. These impactors would have brought water, they would have generated heat, they would have added to the atmosphere, but how that all ties together is, it's a good question.
I have a question for you more personally. If you would tell us, please, why did you decide to study the moon?
Well, I feel like I got really lucky. I was a physics major for a while in college, physics and astronomy, and I just didn't enjoy it. The research I was doing was just, yeah. So I talked to my advisor, who was very understanding in the physics and astronomy department, and he told me, you're interested in space, but this isn't for you. You should go talk to this guy in the geology department. He does NASA stuff. And that's all he knew. So I went and talked to this guy, and he was at the time working on the Near-Earth Asteroid Rendezvous mission. And so that was the first orbiter of an asteroid. And so I got a summer work-study job helping out with this mission. I got to sit there piecing together different images, creating image mosaics of this asteroid. And this was, I thought the coolest thing ever. I was the first one to get to see these images. I got to help with the data processing. I got to, eventually they let me start targeting, like, ooh, I saw this cool thing here. Can you please take another picture of that? So and then once I started taking geology classes, that's pretty amazing being able to kind of look back that far in time and understand what happens early, not just on the Earth, but early in the solar system. So those two combined, plus I was really into photography at the time. So it all came together in a great way.
Earlier you had mentioned a great deal of interest in discovering water. I'd like to know your perspective on other types of things that might be of interest on the moon.
In terms of like a resource?
Yes.
Yeah.
Specifically mining operations, we've heard a lot about.
Yeah. Well, right now, the biggest interest is in mining water because water is super valuable once you get into space. Launching water off the Earth is really, really expensive. And so if you can essentially put, like a fuel depot on the moon, so instead of having to take, like you're driving across the country, you have to take all your gas with you. Actually, like the moon can be like kind of a little pit stop there. But there are other things people are interested in. I mentioned that the moon has a lot of titanium in the rocks on the near side. The problem with the mining, even for the water, is that we don't really know yet how feasible it is to mine them. We know that there is some amount there, but it starts to get into this other realm of like economic geology, where you understand if it's really a true resource, something that would benefit. It'd be cheaper to use there instead of bringing it with you, or it'd be cheaper to go get titanium from the moon and bring it back to Earth instead of mining for it on the Earth. So that starts to get into a whole other realm that, is beyond my expertise. But if you're on the moon, there are a lot of potentially valuable resources.
does the moon's gravity make the volcanoes act different than on Earth? Does the lava flow different?
Oh, that is such a great question. So the coolest way is in these eruptions that are called fire fountain eruptions. And we have fire fountain eruptions on Earth. In Hawaii, for example, there are eruptions that have a higher gas content, like water or various volatiles. And so that means that when they're deep in the Earth, they're fine, but once you get to a lower pressure, they start to explode. And you get these huge fire fountains of eruptions. So if you take that to the moon, where the gravity is 1/6 lower, there have been these enormous explosive eruptions on the moon that essentially littered huge, hundreds and hundreds of square kilometers with these glassy beads. Because when you're erupting explosively into a vacuum, all of the lava quenches into a glass. And so we have these incredible just like fields of volcanic glass beads. And that's my favorite way. That actually ties into some of the mining, because those glass beads typically can have some amount of water. Some of them are titanium rich. And so people are really interested in understanding those more, sampling them to understand what you can do with them.
I've got time for one more question, and I'm going to grant it to the head of the Astronomy and Astrophysics Research Lab at the museum, Dr. Rachel Smith.
Well, that's not fair. All right. Well, my question was, when I understood that the Apollo astronauts were trained, and this is not based on recent really information, but were trained to differentiate between impact craters and volcanic craters. And I'm wondering if that's changed. I had thought that they only saw evidence for impact craters, and it sounds like there's a lot of evidence now for volcanism. So can we tell the difference now? And is there evidence for volcanic craters specifically, and especially the one when you showed the slide of water and you said it could have come up from volcanism, I guess.
Yeah.
But how are we kind of like piecing together this puzzle of volcanic versus impact?
Yes. So a lot of that now is coming from both combining compositional data, what these deposits are made out of, with really high resolution morphology, looking at their shapes. So for example, I showed the two domes. We thought for a long time, based on their shapes, their domes, one of them has a little crater at the top, that they look like volcanoes. But it wasn't until more recently when we had the compositional data to show, wow, these are really distinct from everything surrounding them. They're really rich in silica. There's no way this is at all like impact related. So that is one way. Talking about water with volcanic deposits, that goes back to the same thing, the glass beads. We do have little bits of beads within some of the Apollo soils, and for a long time we thought that they were completely bone dry. The moon was devoid of any water, but as technology has advanced, some of the more recent researchers have been able to look and find water within those little volcanic glasses. And so that's one of the cool things that they're doing now, just opening up some of those samples that have been stored in a vacuum or a nitrogen purge for the last 50 years, because they were set aside. A huge amount of the Apollo sample collection was set aside for, some of it for now, because technology has advanced so much that now we have these pristine samples. We can go back and test them, open up those tubes, see are there volcanic gases that escape or volatiles that were trapped on the moon's surface that escape. We could measure those. And the same with really any sample return mission. That's what I love. It's really annoying when you're planning a sample return mission and they tell you, okay, well, just remember 2/3 has to go for curation. We're just going to lock it away in a vault, 2/3 of any sample you bring back. But technology does advance, improve, and then one day you'll make more use of it.
Thank you very much. One more round of applause.
Thank you.
Fantastic job. Thank you. Yeah, cool stuff. Did you learn something new? You learned a lot of new stuff tonight, didn't we? Yeah, so you know what? Thanks everybody for coming out to the Science Cafe tonight. Don't forget, if space is your thing, we've got another Space Cafe coming up in July, all celebrating the 50th anniversary of Apollo, all part of Liftoff NC. You've got the calendar of events. I hope we'll see you back here again sooner than that, though, for more great topics here at the Science Cafe. Do not forget, please, if you like science and you're here, so I know you do, there is a way for you to participate in the science project right now, and it's that survey on your table. It shouldn't take but just a few minutes for you to do that, and you can leave it right on the table. We'll come around and collect them once at the end of the night. So thank you so much. If you've got questions, you can find me or the person in the red shirt can answer questions about it. And if you need a survey to fill one out, we'll get one to you. Just wave if you need a survey. And hey, thanks for coming out. Good night, everybody.